And I've been in this field working on climate change and geoengineering for 7 or 8 years now, and it never ceases to depress me just a little bit every time I listen to these sort of speeches and how hard it's going to be to get to the next stage, to get to zero, to move in a direction where we're not continuing to do more and more damage to the climate system. So Armin has already set this up really nicely by depressing you all to bring you to the same point of, okay, my God, what can we do? What is Plan B? What are some of the conversations about Plan B? And that's what I'm going to talk about here to sort of set the stage on what is geoengineering, some of the science and core policy issues of engineering our climate system. So let me start with just sort of very quickly covering, sorry, I'm going to screw you up by walking around while I do this. Let me start by just mapping out the responses to climate change that you've already talked about a lot through this course, and Armin has done a good one to begin with. Mitigation, reduce human impacts on the climate system. That's the basic concept of mitigation. What we're doing is bad, we should stop doing it, we should let Mother Nature do what she's done for billions of years and it'll be better. The second alternative is, since we've already started screwing it up just a little bit, we can alter human systems to suit the changing climate, because it's going to change around us. If we don't, it's going to hurt. There is another option that John Holdren, the chief scientist for the US government, has labeled on here, which I don't have, which is suffering. You can choose not to mitigate, you can choose not to adapt, and then people die and suffer in other ways. The sort of story, the narrative that Armin gave about the challenges of trying to mitigate, of trying to get to a stage where our emissions are low enough that we're not damaging the climate, and the challenges of getting political agreement. He went through some of the technological challenges. What Armin didn't cover, and I think John will talk a little bit about, but to put it in perspective, it's not just about the technologies, it's about getting people to agree to use the right technologies, to break some of the political structures or some of the market incentives that have led to the type of energy system we have. We don't just have the energy system because fossil fuels are cheap and we like burning oil, we also have them because of the political societal structures, and that's quite difficult. Now, with all those challenges, it led us a variety of scientists around the world to ask, well, okay, if we can change the climate in a way that makes it worse, couldn't we change the climate in a way that makes it better? So geoengineering is the basic idea of, rather than altering human behavior to suit the changing climate, how about alter the changing climate to suit the human systems that we have? The human systems have evolved in a period of geological history where the climate has actually been incredibly stable for the last, particularly the last several hundred years, but even if you go back thousands of years, 10,000 years, for most of what we consider to be human advancement of society and civilization, the climate has been remarkably stable by comparison to what it's been in periods beyond that. So even if we weren't changing the climate, 10,000, 5,000 years from now, the climate may, from a variety of natural influences, change in directions that would be bad for society anyways. So some of these questions, actually, the basic idea for geoengineering dates back to some of the conversations about terraforming. If you wanted to live on Mars, it's not very habitable right now, but what could you do to make it habitable? So that's where a lot of these ideas about altering the climate come from. Now, geoengineering, the definition, it should be more accurately called climate engineering, to make it clear. This is about engineering the climate system, about trying to put dials and knobs in the climate system that are more controlled than the ones that we've been accidentally changing now as a side effect. And there's two components to this. Geoengineering, by definition, is the deliberate and large-scale engineering of the climate system. Now, on a small scale, look around. We engineer our systems all the time. This climate inside this room is an engineered version of the climate because it may be raining outside. I'm not sure. I haven't been out. I live in London. It rains all the time there. I quite enjoy the engineered environment. But it's not at that large of a scale. The large-scale component of this is starting to look at the scales of regions through global, altering the climate system at the same scale at which we're altering it by dumping carbon into the climate system. Now, there are two types of geoengineering that have been thought about. This here is a map, a very simple energy flow for the climate. You've got the sunlight coming in, some bit of the sunlight is reflected away by clouds and reflective parts of the surfaces. Some part of the sunlight is absorbed, whether by the oceans or the surfaces, warms the climate system up, and then the bits that are absorbed get re-radiated back out into space. And you end up with the greenhouse gases. As we dump the greenhouse gases into the atmosphere, that changes this portion of the system. It changes the long wave radiation, traps a bit more of it, warms the planet up. And as you can see here, this is just a nice little map of the wavelength of the radiation that is coming in and going out. And you can see it's two relatively distinct bumps within the radiation spectrum. And the two basic ideas of geoengineering, the broad concepts, are one, to remove the carbon dioxide from the atmosphere. There's other things you put in the atmosphere that cause warming, but the main focus has been on removing carbon dioxide. Armin talked about CCS, carbon capture and storage, and the idea there is you would capture the carbon when it's going out the tailpipe of the factory so that you don't leave it and get into the atmosphere. In that pipe, it's actually, the gases can be as much as 50% CO2. Once it gets out of the pipe and it gets out into the atmosphere, it actually becomes very diffuse. If it was 50% carbon dioxide in this room, I wouldn't be able to talk like this. You wouldn't be sitting here. But once it gets out there, it becomes much more diffuse. There are a range of ideas, which I'll show you a few in a minute, for trying to capture it back out of the atmosphere. If you can't stop it from going in, can you take it back out? The other set of ideas focus on the energy that's coming in from the sun to begin with. If the sun is what's heating us up and warming us up, then if you turn the sun down just a little bit, prevented some of this energy from coming in, it would cool the planet down. Now, the idea of sticking a dial on the sun, we realize that's probably at least a few 100,000 years away in our engineering capability, but there are some interesting ideas for how one might do that. Let me give you a few examples, some concrete examples of the technologies being discussed. Let me start with carbon dioxide removal, the concept of artificial trees. Now, these things look nothing like trees. These are my colleagues, David Keith, he's just at Harvard down the road now, Klaus Lackner at Columbia, and these devices are designed to have chemicals flow through them. So as you would basically stick these things in a field, you would blow air through them, and the chemicals that would drip through here would absorb CO2, it would chemically bind CO2, and you often use things like sodium hydroxide, which would bind it, and then you would try and regenerate the chemicals such that you could continue to flow them through and absorb CO2. Let me give you some perspective on the scale of this sort of intervention. This stuff works. We actually use these sort of technologies in submarines and space shuttles, because in submarines and space shuttles, if you use up the oxygen, you kind of need to get it back and get the CO2 out. But it costs, in the stuff we do in submarines, costs on the range of $10,000 to $30,000 per ton of CO2 in terms of investing cost on these things. That's a little bit prohibitive in terms of doing it on carbon markets. Last time I checked, the EU was back at around $3 a ton, so we're out by a few orders of magnitude. To do this, there are some very interesting debates about what the actual cost of this would be. There are some people who are arguing it could be as low as $20 or $30 a ton. Other studies have shown it would be $1,000 or more per ton. I tend to believe it's somewhere, if you built it right now, it's probably around $500 a ton, but that doesn't mean it can't improve over time with more research, big questions. But if you use this technology and you wanted to really make a dent in the amount of carbon we put in the atmosphere, it's basically a way of opening up a hole in the bottom of that bathtub that Armin showed you in order to drain faster. If you wanted to take out 1 gigaton of carbon per year, so we put up, just to put it in perspective, roughly 10 gigatons of carbon we emit every year. This is carbon rather than carbon dioxide, but basically to take out 1/10 of the amount we put up every year, you would have to build a structure roughly the height, the width, and 5 times the length of the Great Wall of China. Now, that's a pretty big infrastructure. It's not impossible. It could be a great jobs program, depending on if you want to go in that direction. It could be an interesting investment. It's not impossible, though. When you think about that much material, that's actually well within the sort of scale of some of the mega cities that we're building in terms of the scale of the oil and energy systems. It's not impossible. It is doable, but it's costly. It takes a long time to build that sort of infrastructure. You still have the problems of having to store the carbon once you captured it. You still have to stay, there's all sorts of associated technical challenges, but it's not impossible. Other ideas that have come up, which have been thought about as a way of doing things faster, potentially get carbon out a little bit more effectively, and do it by manipulating current ecosystems to try and absorb more carbon. One is called ocean iron fertilization. This is a picture off the north coast of Scandinavia, where from the fjords here, a lot of the iron that resides in the deposits often gets washed out during the springtime when there's a lot of melt and runoff. And when the iron hits the ocean, it is a missing nutrient that a lot of algae blooms and phytoplankton end up using to suddenly grow. You get these green swirls, all of that is algae and phytoplankton covering mass swaths of the ocean. Now, as they grow, they eat carbon. They eat carbon dioxide just like a tree does. And then in theory, at least the hope is, when they die, they'll carry that carbon down to the deep ocean with them and sequester it at the bottom of the ocean. And so this led a lot of scientists to say, well, couldn't we do this? Couldn't we dump iron in the ocean in other places where it's missing, grow big phytoplankton blooms, and have it go to the deep parts of the ocean? It's a great theory, but try and track whether or not that carbon actually goes down. Because when these things go down, they actually get eaten by fish. The fish get eaten by bigger fish. The bigger fish get eaten by bigger fish. And what happens to fish poop? Does it float or sink? Well, that's a really interesting scientific question if you're interested in carbon sequestration, but it's actually one that's incredibly difficult, and it depends on where and temperatures and all sorts of. So tracking whether or not this carbon actually stays down has been one of the biggest difficulties of knowing whether or not this is going to have any effect. So the challenges with the CDR techniques, I haven't gone through all of them, this is just a few of the most prominent ones, is that there's a lot of uncertainty around them, they're high cost, and they take a long time, but they at least remove the carbon. Examples of SRM. There are ideas for having ships go out in the ocean and spray sea salt particles to grow clouds, have the clouds become bigger and whiter, more reflective, such that the bit of sunlight that is coming in and getting reflected by the clouds would grow up, would expand. It would, as it goes up, you would end up reducing the amount of radiation that's absorbed by the ocean. You'd therefore cool the planet a little bit. The most prominent one, though, is stratospheric aerosols. Rather than putting it in the cloud where it goes up into the clouds and then it'll rain out again within a week, because clouds have a tendency to do that, if you put it above the clouds, if you put it up in the part of the atmosphere called the stratosphere, it stays up there for much longer. In 1991, Mount Pinatubo erupted. And when Mount Pinatubo erupted, it injected 10 million tons of sulfur particles up into the stratosphere. Those sulfur particles basically acted like little mirrors. Those they reflected a little bit of light, and that light, just like the haze that we used to see over LA and you still see in Mexico City, reflected the light back into the sky, cooling off the planet. And this is a measurement. The top graph here shows between 1991, when it erupted, and 1995, the amount of aerosols in the stratosphere. That's easy to measure in terms of optical depth, and the global average temperature. You see the aerosols went up and they gradually fell out over time, and the global temperature average dropped by 0.5 degrees centigrade at the peak of the aerosol concentration. 0.5 degree centigrade. That's roughly a degree Fahrenheit from a volcano going off. Now, of course, these aerosol particles fell out because when you put them up there, they don't stay, they're going to sediment. But this led to scientists going, well, if a volcano can do it, surely we can put particles up there. And they came up with all sorts of interesting ideas for how to do that. The idea of putting a nuclear bomb in a volcano, thankfully, didn't go very far, but there are other ways. One of my personal favorites is the Howitzer. If you point this gun straight at the sky, it will fire a shell to 50 kilometers. Now, you have enough of those guns firing shells, and if the shells can spray sulfur particles, if you do the back of the envelope calculation, the thing that becomes a little gobsmacking is it would only require 10 to 30 of these guns pointing at the sky, firing a shell a minute, which is well within their firing capacity. If you did that and you could get the aerosols to disperse, you could cool the planet by more than 1 degree or 2 centigrade. The cost of that is incredibly low by comparison to a lot of the costs that we've been talking about on these things. And of course, the gun, as much as it's entertaining, is actually not the cheapest way of doing it. These things are. We build airplanes all the time, and actually airplanes that fly at slightly higher altitude are easy to design. You put a spray nozzle on the back end of it, presto. You end up with, I'm summarizing actually what could be a very complicated process. There's a lot of uncertainties about how particles would come out the back, what size aerosols they would form, how these aerosols would move around in the stratosphere. There's a lot of uncertainty about this. But we do know that Mount Pinatubo cooled the planet by 0.5 degree centigrade, and we know that if you put haze up in the sky, it is going to cool the planet down. The basic concepts are there, and over the last 5 years, because of all of the politics, because of all of the recognition that the climate system is starting to demonstrate how bad climate change already is, never mind how bad it's going to get, it has led to a recognition that Plan B might actually have to be something like this, or these technologies might need to be leveraged. It gets scary, though, when you're talking about costs of maybe $1 billion, maybe $10 billion, but on the order of $1 billion to $10 billion a year to cool the planet by several degrees centigrade. This is within the cost of individual countries. This is within the cost of many individual countries, and you can buy these planes from Boeing and from other places for fractional costs. These are the sorts of things that suddenly could be a political game changer. I know John's going to talk about some of the national security implications of this when individual countries can change the climate system. This is quite different from I know you guys have spent some time in this course talking about the challenges of climate change and the collective action problem of trying to get everyone to agree to cut their carbon emissions. This is the opposite. This isn't a collective action problem. This is the problem of unilateral action, individual actors. There's even been proposals that individual corporations or rich individuals, Bill Gates got something like $60 billion. That's 60 years worth of this. It starts to get scary. Now, there's all sorts of politics and all sorts of reasons why Bill Gates would probably get shot down if he tried to do it, but it does raise all sorts of political challenges. And of course, it's not just political challenges. If this technique just cooled the climate system down and just put us back to where we started with the climate system before we started putting carbon in it, we'd probably already be doing it. But of course, we don't know that. When Mount Pinatubo cooled the climate system down, it didn't just cool the climate system down with no other changes. There were changes in precipitation patterns, where rain falls. When you warm the planet up by adding CO2, a blanket that warms it up, and you cool it off by turning down the amount of sunlight that comes in, sunlight landing on the ocean actually causes evaporation of water. It causes the sort of transpiration that leads to precipitation patterns. So if you warm it up by turning the average temperature up lightly, and you cool it down by turning the light down, you change where rain comes from, where rain goes, and we seem to have built our agricultural system based on where the rain is now. So when you start shifting that around, that can become quite political. And this is just one climate model. Climate models are not good predictions of the future, but they are very good at telling us things that we need to worry about. And these brown spots are areas where, according to some models, you end up with decreases of precipitations in particular scenarios. And you see little brown spots in annoying places like sitting over Northeast Africa, where Ethiopia has had famines recently. You see it sitting over, that's right, the areas of Indonesia and India that require the rain, the monsoons, in order to grow all of our food that feeds something on the order of 2 billion people. It gets a little problematic when you start turning the rain off for 2 billion people. So these are the sorts of uncertainties around there is a lot of climate modeling going on now. There's a lot of attempts to understand whether or not these very early climate models are actually telling us something real or whether there's anomalies. There is increasing climate modeling to try and understand this, but there are a lot of scientific uncertainties. Of course, I say that. I would also emphasize there's a lot of uncertainty around what the climate models tell us about climate change. We use the same models to try and understand how the climate is going to change going forward just based on CO2. All these ones do is add in an additional perturbation. And there is some evidence to say these future worlds may be, even though they may have uncertainties and may have unintended consequences, the net damage may be less in a geoengineering plus climate world than in a climate change only world. Now, again, this is a matter of perspective. There's all sorts of uncertainties that need to be researched, that need to be dug into. This is only, the real research into geoengineering as a scientific field in question has really only started to emerge in the last 5 years. In the early 2000s, it was still a taboo subject to talk about this because the idea of intentionally engineering the global climate system, well, it's scary. It brings up sort of, my God, are we actually talking about making Mother Nature a cyborg? That's a pretty big question. Has a lot of ethical implications, has a lot of cultural implications. But yet, the desperation that scientists have started to feel in the last half decade, the last 10 years, is a recognition that we're having some significant problems with trying to get agreement on reducing the impacts. And when you've got cancer, chemotherapy suddenly doesn't start to sound necessarily as bad as it did when you're a perfectly healthy person. That's at least my perspective on it. I've already basically said what's on this slide. I'll just summarize it quickly. There are essentially 3 parameters that, at the simplest level, you care about the most. The ability of any particular intervention to counteract, to reduce the sort of climate change that's already happening. The technical feasibility and cost, can you actually do it, or is it pie in the sky? I mean, the idea that Armin presented of putting biodegradable white reflective materials in the Arctic, is it feasible and doable? Well, potentially. Those are the sorts of things that you've got to ask questions about. Timescale. How quickly could you deploy these things? How quickly do they have an impact? And again, that links back to the feasibility and cost. It would be hard to imagine that we're going to build something at that 1 gigaton of carbon scale, 1 billion tons of carbon, 5 times the length of the Great Wall of China. We're not going to do that in a month. It's unlikely we're going to do that in 5 years. It's going to take time. Whereas flying an airplane in the sky and spraying something out its exhaust pipe, that's actually feasible to do in a very short time scale. So in terms of carbon dioxide removal, I already sort of mentioned, if you remove the carbon from the atmosphere, that's pretty good on counteracting climate change. You're removing the cause of climate change. Technical costs and feasibility, not so clear. And the time scale is decades plus, certainly to have any major impact on reducing the rate of climate change. Solar radiation management, on the other hand, the stratospheric aerosols reflecting light back into space. Well, start on this end, reasonable time scale. Mount Pinatubo did it, it erupted, and a month later it was cooling the planet. Short time scale is definitely feasible. Costs $1 billion a year to get the airplane fleet. This is an airplane fleet of maybe 20 airplanes. This is a very small fleet compared to airline carriers. This is sort of a small state-level airline company. You're not even talking about one of the big ones at that site. But there's a lot of uncertainty in what the net climate impacts would be. So what does all this mean? Well, actually, let me talk very quickly about research before I jump to the governance. There are various stages of research. That poll at the beginning sort of started to get you thinking in that direction. We'll ask you those questions again after John's done talking, and we'll see if your minds have changed. The idea of doing computer modeling is sort of the first stage. There's been computer modeling going on for quite some time. It's running climate models, it's asking questions. Now, there are some risks associated with this, not in terms of damaging the climate, but there's the idea of moral hazard, or the idea that if you start talking about geoengineering, if you start talking about there being a plan B, does this give corporations and governments an opportunity to say, oh, we'll solve that problem down the line. We'll have geoengineering in 20 years, so we don't need to reduce carbon now. Armin, those were great ideas for mitigation, but actually don't worry about it. $1 billion a year will cool the planet. Those are narratives that you could see emerging, even if all you're doing is a little bit of research on computer models. Then there's the question about technology development. When you start building technologies in labs, exploring what they do, it introduces interesting questions about who owns the technology. Do you want countries owning the technology, corporations owning the technology, militaries owning the technologies? Who has the IP? Who has control over the decisions that eventually come about who uses the technologies and how? Then comes the testing. It's great to build a technology in the lab, but if it's only in the lab, it's not actually going to tell you much about what it does to the real world. So if you want to go out there and start testing it out, you can start with subscale field tests, sort of, I'm going to spray a little bit of aerosol out the back end of my pipe just to see what particle sizes are, see what it does to reflect light, but it's not going to have any real climate impact because it's way too small. Somewhere in between that, though, and actually deploying a large-scale intervention, there's all sorts of challenges. There's all sorts of uncertainty about, how small is small? Is 1 kilogram small? Is 1 ton small? Is 100 tons small? Is 1,000 tons small? At what scale do you start having enough of an impact on the environmental and climate system that you can start testing more and more stuff, but you're starting to have more and more risks of impact? And then, how desperate is the situation now? Armin talked about the fact that the Arctic is already changing way faster than the rest of the planet. The sea ice is disappearing at a phenomenal rate, way faster than our models predicted 5 years ago. And the consequences of this are still yet to be understood. That one of the talks that was most scary that I've seen recently was discussing the fact that hurricanes like Hurricane Sandy that have gone on for centuries come up the East Coast and then hooked out and gone out into the ocean. That's the normal trajectory of hurricanes like Sandy. But the reason why things have started to change is when you warm up the Arctic, you no longer have the heat going in different directions. It now is cooler for it to go away from Greenland than it is for it to go out over the ocean. And as a result, more and more hurricanes are going to hook in and come into this sort of area of the world. That's a scary phenomenon, but it's just one example of the many sort of changes that you can end up happening because of the changes in the Arctic. Are we at a stage now that it's worth taking the risk of cooling the Arctic down by 1 degree centigrade? I don't know. That has all sorts of social, political, environmental impacts that are all rolled together. So 2 obvious questions that this is hopefully priming in your mind. One I've already mentioned. Will even talking about geoengineering or solar radiation management reduce the motivation to mitigate, reduce investment in adaptation? It might, we don't know. It also might just scare the hell out of people so that they decide, you know what, we don't want people building these things so that we end up using them. So it's uncertain how that goes. And there's a lot of interesting social science data coming in that suggests people split in very different ways. And who will control the global climate? Who will have a choice as to whether these technologies are used or not? Is this a button on President Obama's desk? Is it a button on the Politburo's desk in China? Is it an international organization? Is it a city that's getting just completely destroyed by climate change and decides, even at the city level, they've got the money, they need to do this? Who will make the decisions? These are critical questions, and we're coming up on some of them now. I think John's going to deal with more of this as well. But I would also say that there's a first step to governance. It's not just about governing the whole thing and the future of managing the climate system. The first thing is we have to govern the research. As research is happening now, if it's developed in labs that are controlled by corporations or militaries or universities or the public sector, all of those lead to different outcomes, different interest groups, different structures for the governance of research will lead to different futures, different path dependencies. And as they play out, thinking about the early governance right now lays a foundation in the way we govern research in order to set the foundations for better governance in the future. Key questions to think about, and I'm going to go through these quickly because I've run a little long. Key questions are about legitimacy, at least as far as I'm concerned. Who should decide? Who will decide if and when to conduct research? Whether the generated knowledge should be in public domain, how it should be regulated, and if and when the technology should be deployed. And there are a whole range of communities that need to be involved in this discussion. I've been trying, as part of my work, to organize some of these. Places like the Royal Society in the UK have been key in trying to organize these sorts of discussions, but more are required. And I'm going to skip through this quickly, but these are just a few examples of the type of research that are already going on very controversially. I'll just talk about it. This is a balloon experiment that was called the Stratospheric Particle Injection for Climate Engineering experiment that got canceled because of a range of questions about IP. Who would control the IP coming out of it? Some experimenters have taken out patents, so as a result of it, it got canceled. This is an experiment that no one really noticed, the Eps Experiment, which was designed to do science on how aerosols affect clouds. All they wanted to do, the core of the project, was to inject aerosols and see if clouds grew or not. But that has a use as a technology for geoengineering. Finally, this last summer, a business entrepreneur working with a small village on the Haida Gwaii Island off the coast of British Columbia dumped a huge amount of iron off the west coast in what they called an experiment to see if they could grow salmon stocks back, which was the largest ocean iron fertilization ever done. They covered a 10,000 square kilometer dumping area with iron. And the result of it was, you can see here, this is the coast of British Columbia there. All of these ripples are the iron, the result of the iron and the bloom. These lead to the sort of questions, and I would just say a quick caveat, these are only the beginnings of these technologies. There's all sorts of ways these technologies will evolve as this discussion goes on. This is 5 years in. Imagine what the discussion about computer technology was 5 years in to after you invented the transistor. This is the early days of research into these sorts of technologies. So how we set up governance will matter a lot. And from your talk already, or from the course already, you understand about the dimensions of energy and food security, biodiversity, human security. All of these issues are going to be interconnected to the governance discussion about geoengineering. Which of these issues, which of these reasons are going to drive a decision to use or not to use geoengineering? Which groups are going to coalesce to say, yes, for food security, we should do it, but no, for biodiversity, we shouldn't? What do you do to reconcile those? How do our governance structures deal with the sort of group of the emergence of different interest groups around trying to protect these diverse issue areas? What about economics? What about the potential for corporations to say, we want to keep burning fuel, let's just do some of this because we want to use up our coal reserves? There's a whole range of actors at different levels, from the sub-state through international, that are already getting involved. And there's a whole range that are already involved in the international climate discussion. But the questions are, how do we start moving these into a governance arena that starts to deal effectively with the current governance gap? The governance of research, the governance decisions about who should be doing what research when, who should have access to the output of the information, who should control the technologies that are generated. Right now, this is at the early days where we don't have good answers, but it's the right problem, I think, to be thinking about. And it involves all of the actors and the issues and the institutions that you've heard about throughout the course that are involved in the broader climate conversation, but also conversations about human development, about poverty alleviation, about energy access, about food security, about I could keep going. And the question, this is underpinning a lot of what geoengineering raises. The geoengineering technologies themselves are challenging to understand the science and what they're going to do, but the governance of them, how we're going to decide when, if, how to use them, who's going to have their finger on that button. That, for me, at least for me, is probably the quintessential question, and is a perfect point to hand off to John, because he's now going to scare you with some of the international security dimensions of it, I think. So, thank you.